It's really a pleasure to be here for more reasons than one. I've been sick for the last 2 weeks, so I wasn't even sure I was going to make it, but thank you for all my backup hitters that were ready to step in if I didn't make it. I want to tell you a little story today. People often ask me to talk about the future, and I usually have an unfair advantage because you see, I actually come from the future. So let me explain what I mean by that. I've been working at GE Global Research now for 30 years, and they pay me to work on the future. Now, anyone who has ever tried to create an idea and bring it to full implementation knows that it doesn't happen in 6 months, it doesn't happen in 12 months. It more likely takes 10 or 15 years to go to full scale. So the things that I'm going to talk about towards the end of my talk are things that I've been working on, my group's been working on, GE has been working on for 20 years or more. So I'm very, very convinced that these things are going to happen. Exactly how they're going to happen is up to everybody in the audience here. So I'm going to talk a little bit about the things that I think influence the evolution of huge, complex systems. And maybe at the beginning, I should explain what I think about complex systems. Complex systems are systems that are not deterministic. You cannot totally predict their behavior. And I think that's really what we're talking about when we're looking at the Internet of Things, the industrial Internet. People have this great need to try to predict everything. Well, there's certain things that you just can't predict. So you need to have a system that predicts as much of the physics-based reality as you can. And then the parts that you can't predict, you have to have totally different other systems, many of which depend on big data feeds and being able to react and see patterns before anybody else. So I'm going to really talk about my own feelings here today. This is not an official GE presentation, so please don't hold them responsible for the opinions I hold today. I'm going to share with you some of the thinking that I've had over the last few years. And before we go into the future, I want to go back to the past, because I think there's actually a lot of value in thinking through how big, complicated systems evolve. So the first big implementation of the industrial age in the United States started in the late 1800s. This is a picture of what was called the Great White City. It was the World's Fair, the Columbian Exposition of 1893. It was an amazing undertaking by the city of Chicago to try to show that the United States was on a road to be a major player, technically and politically. So they displayed a whole range of totally disruptive technologies at this fair, and they had millions and millions of people come from all over the world in the United States to see it. And it was to celebrate the 400th anniversary of Columbus's discovering the New World. And as you can see, as with most large technical projects, it was a year late. So Daniel Burnham, who was the director of the 10 US architects that were challenged with building a grand and memorable event, designed a huge exposition that was focused on the just magnificent nature of technology like electrification and large-scale equipment that had never been seen before by most of the population. He liked to say, make no little plans. They have no magic to stir men's blood and probably will not themselves be realized. I have lived that mantra all my days at GE. It seems the smaller problems are sometimes the most difficult ones to achieve. He took advantage of the new technical advances that were available in architecture at the time, the steel frame architecture that allows you to go very tall and hang enormous amounts of weight on the structure. But he also made the decision to wrap all this new technology in a very old-fashioned neoclassical design. And it was not without controversy at the time. The fair itself became an emblem of America's exceptionalism, which at the time really focused on the core beliefs of liberty, egalitarianism, and the concept of laissez-faire for business. But all the architects under this big job did not really agree with him. In fact, one of the most outspoken critics was his colleague, Louis Sullivan, who felt that form should always follow function. And although you may not have heard of Louis Sullivan, you've probably heard of Frank Lloyd Wright, who was actually one of the young architects that came out of his office, and probably one of the biggest, most famous architects in the world. And he certainly believed in form following function. So it really came down to, do you want to show evolutionary change with these big projects or radical change? And in the case of this exposition, Louis Sullivan felt that the choice of going with the evolutionary Beaux-Arts, neoclassicism, actually held back the architecture field in the United States for 50 years, maybe more. So it really is important what architecture you choose. Now, at the same time, there was another battle going on at this large exposition. It was the battle to decide how to electrify the company. And there were two competing architectures to do that. G happened to be founded in 1892, the year that the fair was supposed to happen. And the captains of this battle were none other than Thomas Edison, who was the original founder of the General Electric Company, George Westinghouse, and Nikola Tesla. And it was really a discussion between distributed systems versus centralized systems. Does it sound familiar to the discussion we're having today? So it hinged on how quickly you could scale, if you could come up with the killer app, and the price of copper. And the killer app at that time turned out to be an AC motor. And that's what Nikola Tesla provided. He licensed the intellectual property to George Westinghouse, cut a very sweet deal to be paid per horsepower of motors that was created. And the story doesn't end as well, but afterwards, if you'd like me to tell you how it ended, I would be happy to. So the story continued to the point where the AC architecture was chosen because it was much more scalable. DC transformers were very difficult to build at that time. So the result was we changed everything. So we built these networks of electricity and light. This is the United States now from satellite. It allowed us to build high-rise buildings, change the skylines of all the major cities around the world, changed what we considered a reasonable workday, changed the sanitation of all the cities. You can imagine what it was like in Manhattan in the summer with 50 or 60,000 horses walking around. That's why everyone that could get out of the city went north in the summer. And then manufacturing, which was tied to rivers where you had hydropower to power all the machinery, were now unleashed. They could go anywhere. And they did. They left all the areas up along the east coast of North America and went south and west. So it really did change the fabric of society. And now we're at the next step where we're looking at another industrial revolution. And the numbers are just fantastic. They talk about 50 billion, 100 billion. I'll raise it to 1 trillion. Well, let's just go to 1 trillion. And it sounds like a crazy number, but when you think that there's 7 billion people on the planet, if you put a cloud of objects around them, 500 to 1,000 objects, that's 3 to 7 trillion objects. That doesn't seem that unlikely. So what are these architecture choices that we're going to make to connect all these objects? And what is the actual value that we're going to get from this system? Okay, I have a short video. This is the official GE version.
The next industrial revolution is here. It's big iron plus big data, hardware and software, minds and machines. The most profound convergence of industry and technology that will build opportunities and productivity, intelligence and connectivity that could add about $15 trillion to global GDP by 2030. By creating lots of little efficiencies that create fuel savings, better scheduling, reductions in delays and cancellations, more efficient maintenance. It all adds up. Just a 1% improvement in aircraft engine maintenance efficiency can reduce related costs by $250 million annually. Just a 1% reduction in operating ratio could result in a $600 million a year savings for North American railroads. Just a 1% fuel savings in power generation could add more than $4 billion annually to the global economy. It's now a faster, safer, cleaner, more productive world. And it will be greater than what we've ever done before. The industrial internet is here.
A few $1 trillion, that usually gets people's attention. So it does appear that there is going to be an enormous amount of value created. But how did we get to this point? How did the world find itself on the edge of another industrial revolution? Well, companies like GE often react to very large macroeconomic forces. And this is a sketch I made quite a few years ago when I was trying to convince management to look at becoming a software company. We had India going to a digitization model where all IT was rapidly moving to a low-cost provider. So anything you wanted digitized, you could basically go to India and get it digitized. China was looking at becoming the low-cost manufacturing center of the world. They have since now tried to move to a higher tech manufacturing. Europe created the European Union, created enormous open markets, and the US has been focusing on brand and tech innovation for the last 10 or 15 years now. The globalization force is unstoppable, and no one company or country could really influence it. So these are the forces that if you can get hold of and manage for your own benefit, they're just sustainable for many, many decades. Now, the issues that come up with a global supply chain are your business systems become global, and they become very unpredictable. They're non-deterministic. They are susceptible to upsets, oil pricing, for example, regulations, natural disasters. These are all things you can't predict, but yet you still have to manage as you go forward. Now, at the same time as we went global, we had this explosive Metcalfe effect where the value and the cost of computing was exploding in one case and going almost to zero in the other. So there was a race to create larger and larger networks, and we saw this start in the cell phone and telecommunications industry. Bob described the phenomena around Ethernet, but it's applicable to almost anything that has to do with networks. And we saw the cell phone evolve from literally a box that had a handle that you would carry around. It was actually a cell radio when it first came out, to now we have a supercomputer in our hand, and it's more like a brain than a box. And it only took 20 years or so to connect billions of people on the planet. And now we're just starting to address the billions and someday trillions of objects. And GE happens to own or manage many, many classes of these objects. So it's to our great advantage to understand how to build these networks, how to manage these networks, how to create architectures that extract value for both our customers and our shareholders. So as these machines are connected and start to produce enormous amounts of data, there's an irony in all this that actually the information age is now over. So the information age was the time when having the data distinguished the winners from the losers. It was very difficult to get the data, and if you had it, you could protect it, you would often win. Today, data is ubiquitous. Everyone has data. It doesn't distinguish the winners from the losers. It's just table stakes to get into the game. And in many cases, the data is contradictory. You can't even trust a lot of the data. So the war is being fought around intelligence and cognitive systems. And if you don't have those systems in the future, it's just not going to work. So I call this the systems age, and it's going to be complex, and it's going to be non-deterministic. So we're moving rapidly away from Edison's world, where we had two-dimensional network grids, and we're moving into this hyper-networked phase where smart grids and cognitive machines are going to start to control things at, in many cases, millisecond scale, things that humans would actually never do. We've seen this happen initially in the financial services area, and now it's moving into the industrial area very, very rapidly. So digital objects are now going to converse with each other, and they're going to have friends. And a lot of people say, oh, this is ridiculous, computers having friends. Well, I have to tell you, my computer has lots of friends right now. There are probably 100 different friends that this machine contacts on a regular basis. Some of them I know, some of them I have no idea. Whenever it's plugged into the internet, there is a very active relationship that it has. It's uploading software, it's fighting off viruses, it's keeping me from plugging in USB drives. It's really an active system. So GE is totally familiar with network building. Our company, as I'm trying to explain to you, is really based on network thinking. So Thomas Edison in 1878 started his Edison Electric Company, which evolved into the General Electric Company in 1892. And along the way, we've built all kinds of networks. Telecom networks, television networks, electrical distribution networks, distributed power networks, things that have wind turbines, things that have aircraft engines, things that have power systems, things that have locomotives. We have millions and millions of devices around the world that manage trillions of dollars of assets every day. So our role has been to try to eliminate the friction in moving both physical objects as well as digital objects. And that is really our mission. So anytime you can greatly reduce that friction, you unleash an enormous amount of innovation. Now, you probably didn't know GE as a computer company. You know, we make aircraft engines and power systems. But back in the 50s, the Bank of America came to us and said, we have a big problem. There's a disruptive technology that's coming. It's called bank checks. And the amount of manual labor it was taking to do the actual ledger work for bank checks was taking up to 20% of the back office of a bank in the late 50s, early 60s. So we developed a computing system and a magnetic ink system that allowed all that to be automated. And it allowed that industry to really take off. It was the real beginning of fintech, to be honest. And we didn't stop there. My group in particular, during the 90s and the early 2000s, created a number of businesses around tracking physical assets like plastic pellets for GE Plastics. We managed energy usage for industrial systems. We built a number of asset tracking systems for GE Capital. We tracked power turbine components all around the world with electronic RFID tags. We tracked hundreds of thousands of vehicles for GE fleet management. And now we've moved into crowdsourcing environments and digital manufacturing commons, which I'll talk about a little bit more. But it's always been around reducing this friction to data or physical flows and managing and optimizing along the way, realizing that we can't predict everything. So I want to give you some concrete examples of how this was done. This is an example of one of our G Capital businesses that had hundreds of thousands of trailers. And it was a simple problem. Where are the trailers and what's inside them? It turns out there's 3 times more trailers than there are trucks that actually move them around. And people needed to know where all their assets and all their supplies were. So we built a satellite tracking system. And this is back when the cellular network had huge gaps all across the United States. And Walmart used to love to put their distribution centers right in those holes because that's where the low-cost land was. So we developed this disruptive technology for tracking, which eventually expanded to their entire North American fleet, 60,000 trailers. And we became the largest long-haul tracking system in the world. We then used this platform to innovate. We put the tracking system into mobile health units, mobile water systems, mobile energy generators. We tracked the generators as they went into Katrina after the disastrous hurricane there. So at all levels, once you get the right architectures, you can bring in the data and you can rapidly create decisions that mean value for your customers. And you are really striving to build a self-awareness and a type of consciousness in the machine system itself. And the entire world needs this kind of visibility now because of globalization. We've seen it in the big box retailers, but the military needs this type of system. The pharma industry, which is always faced with counterfeits and intellectual property theft, and then the myriad of food scares that have taken us by surprise over and over again. Really, the key differentiator today in the world is trust and reputation. So when we're building the architectures to collect, manage, and make decisions with this data, trust and guarding your reputation is one of the most important things you can do. And William Shakespeare said it best, "He who steals my purse steals trash, but he that filches from me my good name robs me that which not enriches him and makes me poor indeed." And if you think that that doesn't ring true, you could ask Chipotle, or you could ask VW, or there's a long list. When you lose trust with your customers, that is the most difficult thing to get back. Money is a commodity. Trust is unique and it's personal. So we need to track and guard our objects and our systems and our reputation. And if we do it right, we put it together in all these systems that allow real-time data feeds to be combined with the deterministic systems, and we get a hybrid knowledge network that allows us to function more efficiently and with insight that other groups don't have. Now, if you don't think networking is critical, this is an area of the world that has the same people that speak the same language, that have basically the same natural resources. And one group decided not to interact with the rest of the world. And after 50 years, you can see there's basically one light bulb in the northern part of this country. That's Pyongyang at night, North Korea, and South Korea. So that's 50 years of networking or not. So that's quite stark. I don't think anyone can argue that there's a pattern there. Now, what I'm going to say to you is if people do not understand the digital industrial phenomena that's happening now and do not network their machines, it's going to be even darker in a few decades. So this is a do or die for all businesses. We connect or we go into the dark, and it's very dark. So the biggest disruption of all, I think, is upon us, where we're now creating this industrial internet with uncertain architectural detail, and it's meeting up with a renewed interest in manufacturing all around the world. The United States is determined to bring back manufacturing to our shores because of the need for innovation and jobs and creativity, which is associated with that activity. GE cannot resist these macroeconomic forces either. We understand the physical world is evolving at the speed of software. We understand that there is this digital industrial force that no one is going to be able to keep aside. At the 2008 financial reset, our whole company has begun to change. So we have divested about $200 billion in assets from GE Capital. We are focusing our attention on our industrial roots. And obviously, the architectures that we're building now, we have 2,000 people up the road in San Ramon, tens of thousands more spread around the world, building the new digital platform that will link all our machines and our customers' machines in an industrial internet platform. This is the future for us. And when you see a CEO like Jeff Immelt is passionate about this concept, as I said before, I come from the future. When you see these things, you know things are going to happen. The resources are there. He said, if you went to bed last night as an industrial company, you're going to wake up today as a software and analytics company. That is a remarkable statement for an industrial infrastructure company that has been around since 1892. So we are rethinking everything about industrial R&D. The old ways of thinking was basically a linear model, linear architecture. You start with design innovation, you then move to material selection, and then you go to manufacturing. You say, can we build this? Can we find the right suppliers to make this a reality? That's fine if the product life cycle is 20 or 30 years long. That is not the case anymore. All of physical goods and their production is being commoditized as we speak. So we need to move to faster, more efficient ways to innovate and create. And the architecture that we've chosen at GE is a collaborative architecture where we wrap all the individual activities like design, material selection, manufacturing in a software environment that creates a non-sequential process that creates enormous numbers of interactions that don't normally occur in a stovepiped structure, and many, many new degrees of freedom. Now, we have teamed up with other groups to form one of the Digital Manufacturing and Design Innovation Institutes that was announced by President Obama about 2 years ago at the White House. This is a picture of me when I was older and much heavier then. But he announced a $320 million initiative that GE is one of the leading members of. And we are building a digital marketplace, a collaboration commons, where you can use a distributed federated architecture to bring data, models, expertise, simulation environments, test beds, physical equipment from all around the world while protecting individuals' IP rights. This is a totally different way of thinking. GE has over 50,000 engineers, but with systems like this, we can have tens of millions of engineers help us solve the world's problems, and there are no shortage of problems in the world. The good news is there's no shortage of people that want to help you solve them. The problem in the past is there was no efficient way to link them all together. So this is a cloud innovation platform, and we are trying to democratize the basic tools of innovation and manufacturing. We're trying to provide access to tools that were only available to people that worked in big government facilities or big industrial facilities like GE. And we're doing it in a way that's transparent and auditable and automated and totally searchable. So taking all the benefits that we've learned from social media and all the networked solutions that have come out of Silicon Valley and applying it now to the industrial sector. And we don't have to stop at just integrating the software pieces. We can link directly to the physical machines of manufacture. Take, for example, additive manufacturing, also known as 3D printing. We can take all these designs, all these simulation environments, and when we're satisfied we want to try to make one of these, we can deliver it automatically to a 3D printer. And I'm not talking about plastic parts, I'm talking about titanium alloys and all types of exotic materials. So the ability to prototype rapidly has really increased dramatically. But any manufacturer is more interested in production than prototyping. So GE has gone a step further and committed to making over 100,000 3D printed components for the next series LEAP engines. And even since I created this chart a few months ago, we now have over $100 billion of backlog for this new series of engine. So this is not some, oh, let's try it and see how it works out. This is the way we're differentiating with our architectures in this new world that we find ourselves in. And we're not stopping there. We are literally connecting to the rest of the world. These are two optical conduits coming into my laboratory at the Research Center in New York. They have 48 strands apiece. There can be literally tens of terabits per second flow down these cables, and the amount just keeps going up as they slice the wavelengths narrower and narrower. So effectively, we have access to infinite bandwidth now. So the physical world will continue to evolve at the speed of software. And rather than taking advantage of just the compute cycles, which was really what we did based on the Moore's Law phenomena, we now have to start thinking about how to take advantage of infinite bandwidth. That's what's coming next. So the days where everything was constricted and you couldn't get the image or the data sets, and your best way to send a terabyte across the country was to put it in a FedEx envelope and mail it. Those days are over, but I have to say, I don't think most people recognize this. We have started to do things like crowdsourcing, where we had a contest, asked people to redesign an engine bracket. It turns out we got over 700 entries from around the world. The winning design, which used 3D printing, took out 85% of the mass of this part while maintaining the physical properties. You can imagine what that means on an aircraft, because aircraft is all about weight and thrust ratios. So the most amazing thing was this winner had never worked in the aviation industry. So this is an example of how we know that there are millions of people out there that can help us solve problems that we don't either have the time or the knowledge to solve. This happened to be one that was way down on the list. We focus on the hot gas path, the design of the fuel nozzles. These are the critical differentiators in our industry. But why not take out 85% of the mass if you can do it very efficiently with partners? So we are now moving this kind of thinking, this kind of architecture to our factories. We have over 400 factories around the world. And we're calling this the Brilliant Factory Initiative, which will build digital twin ecosystems. These are virtual instantiations of everything we produce, right from the component level up to the systems level. This changes the way you engage your customers, how you think about service. No longer are the parts part of this statistical collection where there's a mean time before failure for the collection. We can now look at each individual part as a unique item, a unique individual that has a birth, a life, and a time when it's taken out of service. It really changes the whole nature of the customer relationship and how you think about services and upgrading and optimization, and we are implementing that as we speak. Now, to do this, we have to connect all our factories, all our suppliers, and people would think, well, why don't you just do it on the internet? Well, the internet, which is an amazing entity, was never designed to do the things it's doing today, as you well know. And today, most of the data that's transferred on the internet is transferred on a best efforts basis. Most of the packets get there, but not all of them. There's no guaranteed authentication. That's why we have all these draconian rules about plugging things into machines and not letting unknown friends interact with me. We have no control over latency or timing or even bandwidth in many cases. So if Netflix decides to release a new House of Cards episode, you could be toast if you're depending on that bandwidth at that moment. So we believe we need something that's more industrial grade, an industrial internet. We're committed to doing that. Now, we're not going to say we have to redesign the entire internet, but we think we do have to add some other features and functions. We need to maintain the basic design principles that have made the internet great: modularity, layering, end-to-end argument. But in many cases, we need guarantees for latency and timing if we're going to control machines at a distance, if we're going to do robotic surgery, if we're going to put machines on the internet that our lives depend on. So the types of things that we want to put on this internet are things like aircraft engines, wind turbine farms, locomotives, healthcare systems. And in order to do that, we realized that GE could not do this alone. One country could not do it alone. So a couple of years ago, I worked with a small subset of colleagues, and we launched what was called the Industrial Internet Consortium. And in just a little over 2 years, we now have over 3,500 members around the world from over 250 organizations from 25 countries. And these include countries like Russia, China, Taiwan, Japan, Germany, France, Britain, Brazil, Chile. We have the attention of the world, and we are trying to resolve the architectural decisions, and the key thing is not technology. It comes down to beliefs. So we all believe that there's hundreds of billions of dollars just for a company the size of GE and its customers if we improve operations in our major verticals by 1%. And trust me, I've never done a productivity program at GE where we didn't get 10, 20, 30% productivity improvements. So this is a very small estimate of the value that's out there once we build out the industrial internet. So do I suppose there's going to be a third industrial revolution? Absolutely. This is a few quotes from one of my favorite authors when I was in high school, Kurt Vonnegut. He actually turned out he was a GE employee after he came back from the war and wrote a book called Player Piano that my son gave to me. And he talked about a dystopian future where machines were starting to become smart enough to replace some of the actual thinking work. So I believe we're at that point in history now where the cognitive systems are coming. I'm actually very positive about the ability to create new jobs if we democratize the tools of innovation, and that's one of the reasons why I'm so passionate about collaboration and digital manufacturing environments. So if we look back, at how architecture can favor certain business models, we saw that in the case of electricity, the design of cities really focused around central power and short network runs. And then the government saw that, well, they're never going to build out into the rural areas. So government policy came in and created the rural collectives. And it was based on a belief that everyone deserved access to power. So we're really staring at that issue again with this new industrial internet network that we're looking at. And I'd like to further look at what creates value. Software architecture, in my estimation, extends far beyond and encompasses the processes and the physical structures into the minds and machines and also of man itself. Karl Marx, before there are any automobiles running around and any large networks, posited that it is clear that the real intellectual wealth of the individual depends entirely on the wealth of his real connections. That's an amazing statement. More true today than ever. Only then will the separate individuals be liberated from the various national and local barriers, be brought into practical connection with the material and intellectual production of the whole world, and be put in a position to acquire the capacity to enjoy this all-sided production of the whole earth, the creations of man. That was in a book where he critiqued German philosophers. So we see that the essential value of data and information is really controlled in large part by the nature of our connections and the patterns that we can see in these connections and the data flows that ultimately come from the connections. The framework that we have is enabled by our economic systems and our policy that encourage certain architectures and discourage others. The behavior of these complex architectural interplays between technology, business, and politics is definitely not deterministic and constantly evolves. And I would argue that complexity itself just abhors determinism. So we have to get out of the mindset that we're going to predict everything. We have to be very comfortable with uncertainty. So the new framework, in my opinion, this next generation internet, has got to be planned out with everyone at the table, because it turns out everyone doesn't share the same beliefs. So if we look at the EU over the last few years, there has been a series of regulations and various political revelations about data provenance, data security, the right to be forgotten. In China, that really values security and protection of its political system. We see the Great Firewall. These societies have very, very different beliefs than what emanates from a few hundred miles up the coast. And if we're going to build a global network that is interoperable and trustable, we need to engage all these parties. So how did we get here? Well, we got here with some amazing design principles around robustness, modularity, layering, and end-to-end arguments. And if you're not convinced that things like technology can't trump the law, think about what happened with Napster and peer-to-peer communication. It basically destroyed the media industry. The laws weren't changed at the time. It's just it was so easy to move copyright material that videotapes and music just became commoditized overnight. There was a futile effort to battle the customers. In fact, there was a case where many companies started to actually sue their customers. That is usually not a long-term strategy. So in the end, it wasn't the law that rescued IP. It was actually a different business model and a different network. It was Netflix, which commoditized the delivery of intellectual property to the point of $9 or $10 a month. That was an amount that was a good price for almost everyone, and you didn't have to worry about the viruses and all the other unknowns of those friendly machines that wanted to connect with you. We see that there are other companies like WeChat and Facebook also now struggling with what is the appropriate architecture and what is the right balance between privacy and networking. And just to highlight the different views of how businesses can be seen, Google often talks about hoping to become the global brain. But some people see it as the embodiment of 1984. Facebook, wants to create companions that we chat with and we talk with. I know a lot of older people I talk to are concerned about their children turning into zombies. Spotify created a platform that delivered free music. Many artists see it as the destruction of their business model. It goes on and on. Apple, the ultimate user interface, or the ultimate tar pit that you just get in and you can never get out. So it all depends on your point of view. Now, what's at stake here? Well, once again, I have to say that architectures are at the basis of how we connect and how our behavior is controlled. And there was a person in the 50s and 60s, Marshall McLuhan, who gave us a view of this about what the network was doing, and he called it, the medium is the message. And it turns out the active structure of how information is provided is actually part of the message, if not the entire message. And it goes to the point where our behaviors are now being modified, not just by what we ingest, but how we ingest it. And if you have any doubt about that, watch people using cell phones today. Their attention span is totally different now. How they interact with media. We had the talk by Daniel this morning. He brought out the physical timer. I brought a couple old devices. Some of you still recognize these. These are random access devices that allow you to rapidly flip through large amounts of data. It turns out, because data has been commoditized, the desire to actually read this entire book has gone way down on average. How many people have read the entire book? Okay, so the people that have trained themselves to read and intensely study, oh my God, another fat one, you want to read this one too? So these are skill sets that most people are not developing anymore. We heard another comment this morning that, oh, there's a 1,000-page manual to describe how to use Adobe, and people just didn't see the value in that. Well, that's true. They don't see the value in reading almost anything that's long now. So our behavior, how we interact with each other and information, is changing. And it's not just a desire. The physical structure of our brain is changing. Hours and hours, day after day, reinforcing certain neural connections, certain neural patterns. We are changing society. So we've just begun. These are the optical paths across the United States that are going to give limitless bandwidth and compute cycles to everybody. So now if we look back to where we came from, is it going to be a neoclassical architecture that we wrap all this new technology in? Or are we going to try to create a form that follows function? What approach is it really going to be? And what are the core beliefs that are going to guide us? Because in the end, I believe we're creating a global nervous system. I believe the beliefs we need to hold dear, it should be interoperable, it should be secure, and it should be trusted. Almost everything else is detail. So I hope you join with me and help build this largest cyber-physical system of all. And I'd like to dedicate these ideas to a brilliant Austrian economist, Joseph Schumpeter, who coined the term creative destruction. And that occurs when you take investment capital and great entrepreneurial ideas and fuse them together in a market economy. And I think that's the opportunity we're looking at right now, a bigger, grander opportunity than we've ever seen before. So thank you very much.
Thank you very much, Joe. And I think we'll take 2 questions. We'll go until we'll take 5 minutes from our break, and then Joe will be here for the rest of the day and tomorrow, and we'll have some time with him for other questions. So we'll take the 2 first questions.
It's quite a future, but I think there's a big educational challenge, both for society as a whole and for us as software professionals. You didn't really address, what do we have to learn to get to where we're going to be
All
when
right,
this
so
stuff is part of the environment?
It's a huge question. It's a very important question, probably the most important question of all. How do we stay relevant through a career that will span 30 or 40 years when everything is changing at this rapid pace? So one of the solutions is to democratize the availability of the information. There's another thing, though, that I think most people don't recognize is the nature of business is changing. We're going to move away from a blockbuster mentality where we need to create products that sell millions or hundreds of millions of units. A blockbuster, by definition, is a product of some average property that most people will find as satisfactory. But it doesn't really truly fit them precisely. So the markets now are becoming very, very broad with enormous tails. And this creates enormous opportunity for individuals to specialize and become creative in their own way. So if you give people the tools of knowledge and innovation and production, and they decide become an expert in a small segment of the market, I believe these platforms that we're now building are giving people the ability to serve markets of one. And I think that is going to be, in the end, the solution where people have access to information, they have access to small markets, and they will fulfill those needs, whether it's in manufacturing or services or communication or music or art. And you can see how what people watch in media has totally changed, from blockbuster movies to YouTube to Instagram.
Okay. I think everybody recognizes we have to go to break. Joe, thank you so much.
Thank you, everybody.
This is a small gift.
It's a great future.
Thank you. Appreciate it. Small gift from